Welcome to an overview of our project about the potential of using geopolymer cement in nuclear waste encapsulation. Radioactive cesium is a waste product of nuclear energy generation that is highly soluble in water and therefore must be contained to prevent its leaching into the environment. Ordinary Portland cement, or OPC, is the material most commonly used to contain cesium due to its physical encapsulation properties. However, OPC is prone to leaching cesium and has a large carbon footprint, representing risks to nuclear energy plants, waste disposal sites, and surrounding community. An alternative material to OPC is a geopolymer cement, or GP, which is formed by the polymerization of fly ash, water glass, and sodium hydroxide. GP has an improved cesium retention since it immobilizes the radionuclides physically and chemically, as opposed to OPC, which only offers a physical barrier. The objective of our project is to design a GP cement with improved leaching resistance compared to OPC, while maintaining sufficient mechanical performance. Making an economically competitive product with reduced carbon footprint are secondary objectives.
Phase 1 of the project consisted of determining the optimal composition to maximize compressive and tensile strength. The ranges for each component, as shown here, were input into a design of experiment software to generate our tests. Compressive and tensile tests were conducted on geopolymer lab samples to collect data. Statistical analysis led us to a composition of 75.5 weight% fly ash, 20.5 weight% water glass, and 4 weight% sodium hydroxide, which maximized mechanical performance. This composition would then be used to conduct the experiment in Phase 2.
For Phase 2, the focus was to determine the optimal processing parameters of setting temperature and cesium content. The software was once again used for experimental design with the ranges shown here. Leachability tests, Archimedes principle tests, and compressive tests were conducted to measure the leaching index, open porosity, and compressive strength. With our data, we maximized the leaching index and compressive strength while minimizing open porosity to determine the ideal setting conditions to be 75 to 85 degrees Celsius and 16 to 18 weight% cesium. Using the optimal composition and processing parameters determined in Phase 1 and 2, we predict a geopolymer cement with a resulting leaching index of 12.7 and compressive strength of 50.9 megapascals. These improvements show that our design is superior to that of OPC, both in encapsulation efficiency and mechanical strength.
After conducting a sensitivity analysis, we recommend that future investigations consider testing beyond our upper bounds of setting temperature and cesium content, which may yield even more promising results.
Geopolymer cement addresses our problem statement by providing a material to replace ordinary Portland cement in nuclear waste encapsulation. This is valuable for managers of nuclear plants and waste disposal sites, as well as the surrounding community. Based on an investigation we conducted for a pilot project in Richland, Washington, benefits include a reduction in carbon dioxide emissions up to 50% and similar or lower annual operating costs. Ultimately, the most valuable result is a reduction in radioactive environmental hazards from geopolymer's superior resistance to cesium leaching. With its unique feature of chemical encapsulation, the surrounding environment and community are safer when radioactive cesium is contained in geopolymer cement. This makes our solution viable in the long term and may even influence the ongoing discussion around the future of nuclear energy.